how do motors work? I wonder. If you ever looked around your house, you'll see lots of things that use electric motors, such as kids' toys, or fans, electric toothbrushes, hair dryers, and this electric cutting knife. Just to name a few. I mean, it is something that most of us use every single day. But how in the world does an electric motor actually work? I mean, it's like you turn it on and it starts rotating. To answer that question, we need to ask ourselves another question. How do magnets work? Let's think about that. So we know that for magnets, opposite poles attract and the same charges repel. Now what if you took a magnet and drilled a hole in the center and then put it on something so it was allowed to spin, like this? Now if you put another magnet next to it, the rotating magnet will spin so that the north side will face the south side, or vice versa. Now if you switch out the side magnet, then they'll start to repel because the north repels north, and that middle magnet will keep spinning. So you just have to keep switching the side magnet north-south, and that magnet will attract and repel and attract and repel, and spin like this. So does that mean in order to produce a motor, we have to keep switching in and out magnets? Maybe not. Instead of using a magnet like this, we can actually use something like this, where we take a piece of iron and wrap some coil around it, a solenoid, and produce an electromagnet. Now if you look back at this last video that talks about electromagnetic induction, you'll find out how that works and how electricity can actually produce a temporary magnet that can be turned on and off with the flip of a switch. So motors basically work by having magnets spin them. And those magnets are produced by something called electromagnetic induction! So if you remember, electromagnetic induction basically states that electricity can produce magnetism, and moving magnets, they have to be moving, can produce electricity. Now there's something really cool about electromagnetic induction. We can change the direction of electricity by simply changing the direction or the polarity of the magnet. So when I move the magnet back and forth, it changes the direction of electricity. Likewise, if I can change the magnet, the electromagnet, by simply just changing the direction of the current. So I can flip the battery around, or flip the wires around. And all these tie in to how motors work, and also which direction motors will spin. So, there are three major topics when it comes to electromagnetic induction, alright? The first one deals with forces, and we're going to talk about that one in this video. And then, if you watch the next video, we're going to talk about voltage, because voltage is very important when dealing with electromagnetic induction. Alright, and finally, transformers. There's more than meets the eye on those. We'll talk about that in the next video as well. But let's start talking about force. This is the FBI! Alright, so we can use the FBI right-hand rule to figure out things about electromagnetic induction. Alright? Let me explain. Here's the equation for force in electromagnetic induction. Force equals B times I times L. Force equals Bill. Alright? So, here's what happens. The amount of force that's applied to a wire, for example, or to a motor is going to be given in newtons. That's the F. F for force. The B is the strength of the magnet. Strength of the magnet is given by the variable B, which is measured in Tesla. So a really, really strong magnet, like this one, is going to have a much bigger B value, or Tesla value, than something like this little dinky magnet here. Alright? I is the amount of electrical current. So if I use more electrical current, I get a stronger magnet. L, finally, is the length of the wire. If I use more wire, I get a stronger magnet because there's more electrons moving through that wire. So, a couple things that increase the force. A stronger magnet is going to increase the force of the motor. Stronger current is going to increase the force of the motor. And more wire, a longer wire, is going to increase the force of the motor, which is why in motors you see a bunch of wire looped up in a small area. called a solenoid, because that's one way to get a lot of wire in a small amount of area. It doesn't take up too much space, and yet there's a lot of wire to work with. So length increases, force increases. Current increases, force increases. And the B, the strength of the magnet, increases, the force increases. So if you want a strong motor, you need BIL. So what's up with this? The FBI rule. Now listen carefully, because this is very important, and the FBI demands that you know this. Well, the right-hand rule for electromagnetic induction is kind of cool because it tells you which direction the force is going to be applied. And the way it works is you take your right hand, it has to be your right hand, and you make a gun with your right hand, like you're in the FBI. The FBI, alright? Now each of these fingers is 90 degrees to one another. This is 90 degrees, this is 90 degrees, and this is 90 degrees. They're all 90 degrees to another. And what you do is, the eye is the thumb, because when you make a gun, you look at your eye. It points towards your eye. The B is the bullet. Boom, 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 boom. That's where the bullet comes out. So the B, the strength of the magnet, goes out this direction. And the F is your middle finger. I'll let you think about that one. Alright? FBI. Let's see how this applies to real life stuff. So let's see how the FBI right-hand rule works for direction. So here I have a magnet. It's hooked up to basically a DC voltage supply, like a big battery. So if you remember about magnetism and field lines, magnets always point from north to south. Magnets go from north to south, north to south, north to south. It's like Santa Claus. He starts at the North Pole and he heads south, right? Where electrical current always flows from positive to negative. It starts from the positive side of the battery, goes to the negative side. So positive to negative, positive to negative, positive to negative, north to south. All right, we're going to use this right-hand rule to figure out what's going to happen when I turn on this battery. It's going to produce something cool. All right, so let's look at this magnet here. This is the north side. This is the south side. So if I use my right-hand rule for magnetism, I go like this, and I can start with the B or the I, it doesn't matter. And I'm going to start with the B here. I'm going to point my finger starting from the North Pole going south. So that means I have to point this way because it started north, it's going south. So basically there's these field lines that are going this direction. So I point my index finger, hey, the field lines are going this way. They're not going this way towards me, or this way, they're going this way, right? Then the second thing I have to do is I have to follow the wires and see where the current is. Now the current goes from positive to negative. So here's the positive wire. It's going through here. Then this is the positive side of the wire. It flows out this way and then back around to the negative. So the current, the positive current is flowing through the magnet like this. It's going towards you. So to make the FBI rule, I do the GUN, the gun, all right? And I point towards the south pole with my index finger, that's the B. Then I point my thumb in the direction of the current. Now if you follow the current, it's starting back here and it's going forward. So that means I have to keep my index finger pointing this way and rotate my thumb so that it lines up with that wire. Oh, look at that. Now let's double check. My thumb's pointing towards you, and the wire is pointing towards you. My index finger is pointing that way, and the magnet is going from north to south that way. The magnet is basically pointing that way. My middle finger is pointing up, so that means when I turn this on, when I turn on the current, there's this force that's going to be acting upwards. Let's see what happens. Watch this. This is cool. Did you see that? Amazing! They didn't even, there's this invisible force and it just kind of went whoosh, like that. It was crazy. Like, it didn't even, what was that? That was crazy. It made it move without even touching it. All I had to do was turn on the electricity and this force, the FBI force, pushed it up. Now I can change the direction of that force by simply just rotating objects, rotating the direction of the magnet, or rotating the wire, or changing the direction of the wire. All that stuff can be used to change the direction of the motor. And think about it, I can also change the strength of the motor by either using a stronger magnet, using a stronger current, or using more wire, a longer wire, like a solenoid. Let's do another example here, a picture example. Let's say I had a circuit like this, all right? And if you remember, this is a symbol for a battery. This is the positive side, this is the negative side. So current's going to run around this way, that direction. And these little X's are telling you the direction of the magnetic field. If you see X's, that means that the magnetic field is starting out here. Here's the North Pole, and the South Pole is behind the wall. All right. If you see dots like that, that means it's starting. The North Pole is behind the wall, and it's coming out towards you. Here's one way to remember it. Imagine you're shooting a bow and arrow, and if I shoot a bow and arrow and it goes into the board, you see the feathers of the arrow. If you see the feathers of the arrow, this is what you see. That means it's going into the board. If you see the tip of the arrow coming at you, you see a point. All right? That's what this is. You see the little circles with dots in them, points. All right? So let's think about which direction would this wire travel if this was the case. Well, the way you do it, FBI, all right? Let's start with the I this time. The current, the thumb. Which way is the current going? Well, it's going up. Then it's going to the right. Then it's going down. So that means I have to point my thumb down. All right? So with my thumb pointing down, now I have to think about where my index finger is pointing. All right? My index pointer is going to point into the board. With my thumb down, my index finger has to point into the board. Remember, you use your right hand. So thumb down, index pointer into the board. That means, well, look at that. This right here, that's the direction that the force will go. Meaning that this wire, without even having anything touch it, will fly to the right with a lot of force. And I can increase that force by getting a stronger magnet or adding more current. Now let's think about if I did this in reverse. If I simply just switch the direction of this and made this a positive side, now the current's going up. I'll keep the magnet the same, but the current going up, use the FBI rule, current going up, magnet going in. Now the force is going to the left. So I can get that wire to move simply by changing the direction of the current. What's one way to change the direction of the current? Alternating current! Oh my gosh! So, there's basically two ways to spin a motor. If you use direct current, then what you need to do is start the motor spinning one direction, and then when it hits a certain point, turn the motor off temporarily, basically have a slight spot where the motor disconnects, and use the motor's angular momentum to keep it moving that way, and then connect the other side of it, kind of like this configuration here. Or the other way to spin a motor is to just continuously move the current back and forth, like alternating current. So hopefully you got a little bit of the logistics of how a motor works. What you need is a magnet, electricity, and some sort of alternating current. Now if you want a direct current, you have to find a way to temporarily turn the motor off and back on again by making it have a slight disconnection and it keeps spinning with angular momentum and it connects again. In the next video, we'll go over voltages, how to produce voltage using electricity, and transformers. So stay tuned, and always, thank you for watching.